Hello guys, my name is Samson and you're welcome to Chemistry with Samson. If this is the first time watching our lesson, please make sure to subscribe to our channel and like and share with others as well. In this lesson, we are going to discuss some irregularities or some discrepancies or some discontinuity in the trend of first ionization energy across a period. We are going to consider the period 2 and period 3 elements. Is that okay? So, discontinuity in the trend of first ionization energy, I.E. that is ionization energy across a period, considering period 2 and period 3 for our lesson. Is that okay? Now, before we dive into these irregularities, first of all, we need to cast our mind back to the variation of first ionization energy across a period. We said first ionization energy generally increases across the period, that is from the left to the right on the periodic table. So ionization energy or first ionization energy gradually increases from the left to the right hand side on the periodic table. It practically means that once you are considering the period 2 element, oxygen will have a higher first ionization energy than nitrogen. And nitrogen also have a higher first ionization energy than carbon. Carbon than boron, boron than beryllium, beryllium than lithium. That is a generalization. Is that okay? But once you consider this generalization, there is one or two irregularities or discrepancies that we need to address as well. Now, we can address these irregularities or discrepancies based on the period 2 and 3 elements using two basic concepts. That is, one, penetration effect, and then two, we can talk about stability of electron configuration. Is that okay? So penetration effects and also stability of electron configuration. And apart from that, we are going to include the ideas of the Pauli's exclusion principle in electron orbital arrangement and also the Hans rule of the maximum multiplicity to explain the stability of the electron configuration. So first of all, we need to keep in mind that the generalization is first ionization energy increases from the left to the right across a period on the periodic table. Is that okay? The first irregularity I'm going to consider is beryllium and then boron. What is the generalization? The question is, between beryllium and then boron, which one will have a higher first ionization energy? Based on the general trend across the period, we could see that boron is expected to have a higher first ionization energy than beryllium. Is that okay? We expect boron to have a higher first ionization energy than beryllium. But is that the case? There is a small irregularity in this trend here that we need to discuss. Is that okay? Now, before we can break down the variation in ionization energy between beryllium and boron, we need to write the electron configurations. So first of all, let's take beryllium, Be atomic number 4. It has a configuration 1s2, 2s2. And then for boron, atomic number 5, it has a configuration 1s2, 2s2, and then 2p1. I'm going to explain this variation in two forms. Is that okay? Now, the first one I'm going to talk about is Pauli's exclusion principle for electron arrangement. According to Pauli's exclusion principle, the maximum number of electrons each atomic orbital can accommodate is 2, and it should be indicated with an opposite spin. Is that okay? My interest here is the maximum number of electrons an orbital can accommodate, and that is 2 electrons. It means that whether it is a 2px orbital whether it is a 2py orbital or a 2pz orbital, the max number of electrons it can accommodate is 2 to indicate satisfaction based on stability. That orbital is full in terms of its electron accommodation. Is that okay? Once we are talking about first ionization energy, we are talking about the first electron to be removed from these two atoms here, their valence electrons, or the orbitals which contain that electron. For beryllium, the electron to be removed will be coming from the 2s atomic orbital, which has 2 electrons accommodating the s orbital. For boron, the electron to be removed is coming from the 2px atomic orbital, which has 1 electron in there. Is that okay? So once we consider the 2s orbital and the 2px orbital, we could see that for the 2s orbital, it has 2 electrons. That is at the max. So it is fully occupied with the electron. But once we come to the 2p orbital, it has only 1 electron, meaning that it is not up to maximum. There is an additional 1 before it can reach satisfaction. Is that okay? So giving the 2s orbital more stability in terms of electron accommodation, it is more stable than the 2p, which is partially filled here. Is that okay? It implies that since the 2s orbital is fully filled here, it requires more energy to remove an electron from an orbital that is stable in terms of its electron accommodation than an orbital which is less stable in terms of its electron accommodation here as well. Which means that beryllium would rather have a higher first ionization energy than boron. Why? Since the 2s orbital is fully filled with 2 electrons, it will require more energy to remove an electron from this fully filled electron here, or electron orbital here, than the partially filled 2px atomic orbital here. Thereby, beryllium would rather have a higher first ionization energy than boron, which go against the general trend here, with boron having a higher first ionization energy than beryllium. That is the first thing I want you to know. Now, for the second explanation, we are going to base our explanation on the penetration effect. How close an orbital is to the nucleus and its influence on the orbital. Is that okay? So once we consider these 2 atoms here, beryllium has 1 s orbital and a 2s orbital. Once you consider the boron, it has 1s, 2s, and then a 2px atomic orbital. Is that okay? Now, in terms of closeness to the proton or the nucleus, the 1s orbital is closest to the nucleus, followed by the 2s orbital, followed by the 2p in that order. Is that okay? It practically means that once you consider the beryllium and then boron, the electron to be removed from the orbital, for beryllium it is coming from the 2s orbital, and the 2s orbital is closer to the nucleus. In terms of its penetration, it is very close to the nucleus compared to what? The 2p atomic orbital. Is that okay? Please, are you getting the point here? Yes. So it means that if I need to remove an electron from the 2s orbital, since it is closer to the nucleus, there's a higher proton influence, attraction on that electrons in that orbital. Thereby, I will need more energy to overcome the proton attraction to enable me to remove an electron. That is, if I'm acting as ionization energy. Is that okay? But since the 2p orbital is slightly further away compared to the 2s orbital from the nucleus, its proton influence is minimal. So it requires a low amount of energy compared to the 2s atomic orbital. Is that okay? So in terms of penetration, to remove an electron from each of these orbitals, you require more energy to remove an electron from the 2s orbital because it is very closer to the nucleus. So you need to penetrate deep to remove that electron, and it requires more energy. But considering the 2p orbital, it is slightly further away from the nucleus compared to the 2s, so it requires a minimum amount of energy to remove an electron from that orbital. Is that okay? Based on these two ideologies, we can boldly say that the first ionization energy of beryllium is rather greater than the first ionization energy of boron, using these two basic ideas as well. Is that okay? We can also try. So please try that of magnesium and aluminium as well. So as a personal assignment, please try between magnesium and aluminium using the electron arrangement. You arrive at the same idea and then you explain it as it is. So if it is a generalization, we expect boron to have a higher first ionization energy than beryllium, but due to the concept of penetration effect and the closeness of an orbital to the nucleus and the proton influence on that orbital in terms of attraction, removing an electron requires much energy, so thereby increasing ionization energy in that orbital. Is that okay? Yeah. Another way to explain this is using the electron accommodation in each orbital. That is applying Pauli's ideology. Is that okay? So the max electron an orbital can accommodate is 2, which indicates satisfaction and stability. So the 2s orbital is more stable because it is fully filled compared to the 2px orbital, which is partially filled. And since this is more stable than this, removing an electron in this requires a higher amount of energy compared to removing an electron in this. Therefore, we can say that the first ionization energy in beryllium is higher than that in boron. Is that okay? So for your assignment, you can try the variation between magnesium and then aluminium across the period 3 element as well. Again, if it's your first time watching our lesson, don't forget to subscribe to our channel. You can share and like as well. Thank you.